Welcome to part 2 of our lecture on improved filters. This lesson focuses on active filters. Active filters use active components such as op-amps or transistors. There are several advantages, let's say, for using active filters over passive filters. One in particular is if you're trying to build a higher order passive filter, you're going to need to implement inductors in your circuit. Now, inductors tend to be very expensive and they're often difficult to implement in an integrated circuit. So often we prefer to use op-amps then, right? So they're advantageous as compared to the use of inductors for these higher order filters. Another advantage of an active circuit using op-amps is the ability to control the impedance levels in my circuit. So if I'm using an op-amp, I have the ability to provide a much higher input impedance, let's say, than I could achieve with something like an RLC circuit. A final advantage is the ability to not only provide the filtering requirement, but also provide a gain through the use of an operational amplifier. That said, let's take a look at an example of an active filter. In this particular active filter, I have an operational amplifier, I have a capacitor C, and two resistors, R1 and R2. I have an input voltage and an output voltage as well. My non-inverting input for this operational amplifier is tied to ground, and I have this resistor R2 in feedback into my inverting input. So this is a resistor in negative feedback for this particular active filter. Since this filter has an operational amplifier, we should point out a potential disadvantage of this type of filter, this active filter. There should be power rails drawn here, right? So I need a power supply to actually utilize this filter. And some could argue that would be a disadvantageous quality of these filters. Let's begin our analysis of this circuit by creating an equivalent resistance. So this capacitor and resistor are in series, so we can add their impedances together to get an equivalent impedance. So R1 plus 1 over J times omega C. That'll be equivalent then to 1 plus J omega R1 times C all over J omega times C. Since this is a inverting operational amplifier, we can describe the ratio, the transfer function essentially, of our output divided by our input. That's going to be equal to minus R2, this resistor in the feedback path, divided by this equivalent impedance. If we plug in for our equivalent impedance, we'll find that that transfer function is equal to minus J omega times R2 times C, so this will be the resistor in the feedback path, divided by 1 plus J times omega times R1, that'll be the resistor in the input path, times C, the capacitor in the input path. Let's rewrite this as minus R2 over R1, so there's our gain term, times 1 over the quantity, 1 plus the quantity, 1 over J omega R1 times C. Thus, this active filter contributes a gain of minus R2 over R1. Since we're ultimately interested in the performance of this filter, let's take a look at the magnitude ratio. The magnitude of V out divided by V in, that'll be equal to my magnitude ratio, which will be a function of an input frequency omega. This is equal to R2 divided by R1 times 1 divided by the square root of 1 plus the quantity, 1 over omega R1 times C squared. One thing that we see is this 1 over omega times R1 times C term. So as a result, our cutoff or our corner frequency, omega C, that'll be equal to 1 over R1 times C. Using that definition, I can rewrite my magnitude ratio once again as m of omega is equal to R2 over R1 times 1 divided by the square root of 1 plus the quantity omega C divided by omega squared. If we take a look under the conditions where the input frequency is much less than the cutoff frequency, then this cutoff frequency is significantly large. So this term is going to start to dominate. And what I find is my magnitude ratio is really driven by R2 divided by R1 times omega over omega C. In the case now where omega, the input frequency, is much greater than the cutoff frequency, this term is going to be smaller and smaller, so I'm going to end up with effectively 1 divided by the square root of 1 times R2 over R1. So my magnitude ratio under these conditions is effectively equal to the gain, R2 divided by R1. So what this is telling me is that when my input frequency is small, that my gain is attenuated. At higher input frequencies, I'll get my traditional gain R2 divided by R1. What this tells me then is that this particular filter behaves as a high-pass filter. These lower frequency signals are getting attenuated, but my higher frequency signals are making it through and are subject to that gain. And it's also telling me that it's a first order filter, right? Because in my description of the magnitude ratio, this would be a 2 times k is equal to 2, therefore k would be equal to 1, and this would be a first order filter. So this operational amplifier circuit here is behaving as an active filter, giving me both a gain as well as the filtering of the lower frequency signals. So it's a high pass first order filter that is comprised of active components. Now let's consider higher order filters that use operational amplifiers as active filters. Here is a very common higher order active filter referred to as a Salem-Key filter. The beauty of the Salem-Key filter is that as long as I maintain 2 resistors and 2 capacitors, I can play around with their locations in the circuit, and I can change the performance of these active filters. Now, the way they're laid out here happens to be a low-pass filter, but again, by rearranging the 2 resistors and 2 capacitors, I can change the performance of that filter. So I could get a high-pass filter, a band-pass filter, and so on. Now, the configuration here happens to be a second-order low-pass filter, and this circuit has a cutoff frequency defined as omega c equals 1 over the square root of R1 times C1 times R2 times C2. Another interesting quality of these Salem-Key filters is that we can cascade them together in serial, right, effectively multiplying their transfer functions, and we can achieve even higher order filters. So cascading these filters together allows me to have a higher order filter, but more specifically, it's giving me an even steeper transition from my passband to my stop band in terms of a plot of magnitude ratio. So this incarnation of the Salem-Key happens to be a low-pass second-order filter, but again, by rearranging your resistors and capacitors, you could achieve different types of filters, and by cascading them, you can get even higher orders.